Today we're going to talk about words and mappings. This is an appropriate area in which to finish our study because it ties together many of the things that we've talked about before. Again, this is the last of the second half of the class, and what we're talking about today is mostly labeled objects, so we'll be working exponential generating functions. And again, as I've been saying each week, there's many more examples in the book than we're able to do in lecture. But we'll consider some techniques from analytic combinatorics and applications to the analysis of algorithms. So to start out, I'm going to talk about what we mean by what is a word in a combinatorial sense. And to do that, let's just review a few of the related combinatorial objects that we've looked at. So for example, we looked at, again, how many binary strings within bits. It seems we talk about this almost every lecture. So a string is a sequence of 0 bits and 1 bits. And with the symbolic method, using ordinary generating functions, we show that it's 2 to the n. Now, that can extend to how many strings drawn from an m character alphabet. Then in that case, it's a sequence of one of the m characters, which is 1 over 1 minus mz. So again, that gives us m to the n is the number of strings drawn from an m character alphabet that has n characters. So how's that related to words? Well, we'll get there. Let's look at labeled objects now. And let's say how many sets, labeled sets are there of size n? There's exactly one label set of size 2, the one that's got 2 objects in it. And actually, of any size n, there's only one labeled set. This is just a little bit of review of what we mean by labeled objects. So we don't consider the order significant, so there's only one set, and we label all the objects. Now, if you want to take ordered pairs of labeled sets of n objects, then what do you get? For 2 objects, you can have a 1 and then a 2, or a 2 and then a 1, or you can have an empty set in 2 objects, or 2 objects in an empty set. So in this case, the ordering of the sets is significant, and then the labeled objects can fall in the sets in these different ways. And so there's 8 different ordered pairs of labeled sets of n objects, and then you can see the answer is 2 to the n. And that's the same as the number of bit strings, and we'll see how that relationship comes through in just a minute. What about instead of pairs, what if we have a sequence of m sets? How many sequences of length m of labeled sets of n objects are there? And we use the word earn to talk about a set. It's a thing that can hold labeled objects. Thinking of it that way, a classical way to think of it is as balls and urns. So really what we're talking about is the number of different ways to throw n balls into 2 urns. So if there's 1 ball, there's 2 urns, 1 ball can go into either one of them. There's 2 balls, it can either both can go in the first or both can go in the second, or they can go in the 2 orders. The labels on the balls are significant, but not the order of the labels within the urn. We put them in the order they went in, but that order is not significant. And again, there's 8 ways to throw 3 balls into 2 urns. So that's a balls and urns way of looking at really the same combinatorial structure. Again, 2 to the n. So now let's look at how we get at these counting results from the symbolic method. And this is just a review of what we talked about in lecture 5. If we have combinatorial classes of labeled objects, then we have these basic operations that we can perform on the classes that disjoint copies are taking ordered pairs, relabeling in all ways, and then the corresponding operations on the exponential generating function give us a symbolic transfer from the construction right to the generating function. And for labeled objects, we extend that to sequences of length k or sequences of any length, giving those transformations on the generating function, or for sets where we divide by k factorial. So a set of objects from a class, the generating function for that is e to the generating function of the class. And also cycles. So these are the basic operations that we use for labeled objects. And so these are the ones that we're going to use now to look at balls and urns problems, or words. Combinatorially, we're going to define a word to be a sequence of m urns that have n objects. And it's the number of ways to throw n balls into m urns. It's a number of, it's a configuration of throwing n balls into m urns. So we want to know how many different words there are. Then we use generating functions. It's parameterized by m, so that's the number of urns in the sequence. So the generating function is the sum of all possible objects, that's configurations, the way the ball could fall, z to the object size over w factorial, and then as usual that collects it together to get us the number of ways that we could get n balls into m urns. And again, we have all these different ways of looking at it. So this is 9 balls into 5 urns, and maybe this is one way it could come out. That corresponds to a sequence of 5 subsets of 9 things, or we could just write out the subsets. Those are all different ways of representing the same combinatorial object. But in terms of the symbolic method to find out this generating function, or how many different ways there are to do this, it's simple. It's a sequence of length m of a set of objects. And it's nothing more than that. So that means immediately the generating function equation is e to the z to the mth power, or e to the mz. And so our number of different configurations is n factorial times the coefficient of z to the n in that, which is just m to the n. Now that m to the n, again, that's the same as the number of strings from an alphabet of length m with n characters in it. And indeed, there's a one-to-one correspondence between words and strings. So a string, as we talked about last time, is a sequence of n characters drawn from an m character alphabet. And since for each of the n characters in the string, there's m different possibilities, there's m to the n different strings. A word is a sequence of labeled sets with a total of n objects, and there's m to the n words. So what's the correspondence? Well, the correspondence is quite simple. What we do is we take a look at the second set, for example, corresponds to the positions in the string where the second character happens. It's as simple as that. There's no 3, so the third set is empty. The 1 is in position 7, so the first set has 7 in it. And the 5s are at positions 5, 6, and 9. And the 4s are at position 2 and 4. So it's just a one-to-one correspondence where the word tells us the position in the string where the character happens. That is, for in the word, if you look at the case set, for every I in the word, the ith character in the string is k. Or vice versa, if you look at the string, if the ith character in the string is k, then you put I into the case set in the word. So the word is just the indices where the letter appears in the string. That's the correspondence. It's very familiar. We worked with strings before, and now we're going to be working with words. And we have this one-to-one correspondence. This is just another way to look at it for binary strings. Looking at the 8 binary strings as words, first one says that all 3 characters are zeros and there's no ones. And the last one says there's no zeros and all 3 characters are 1, and so forth. What's the difference? There's no difference. It's only the point of view. Last lecture, when we were looking at strings, we were concerned about the sequence of characters and about the relationships between one and the next in the sequence, looking for patterns in the string and so forth. This time, we're interested in applications where the sets of indices are important, where it matters how many zeros there are, how many ones there are, and so forth. But really, it's the same object. And strings, we were using OGFs to enumerate. Words, we're going to use EGFs. So that's a difference in point of view and a difference in technique that we use to analyze variations. So again, here's just a summary for strings, which we considered last time. Consider them as unlabeled objects. We used OGFs to enumerate them. Typical string is just a sequence of characters. So the OGF is 1 over 1 minus mz. If there's m characters, there's m to the n of them. For words, we consider them as labeled objects and use an EGF. We had all these different representations. And now when we're doing sequence, we're doing star product where we relabel in all possible ways. And our number of different words is e to the mz, but we get the same result out. So we're going to be focusing on the balls and urns kind of representation in this lecture. That's a brief introduction to what is a word combinatorially.